welcome to this problem walkthrough. Today, we'll be exploring problem number 446, Arithmetic Slices 2 Subsequence. This is a fascinating challenge that combines mathematical intuition with algorithmic problem solving. Let's dive in and uncover the optimal solution together. The problem we're solving is called Arithmetic Slices 2 Subsequence. To understand it, let's first define what an arithmetic sequence is. An integer sequence is called arithmetic if the difference between any two consecutive elements remains constant. For example, the sequence 1, 3, 5, 7, 9 is arithmetic because each consecutive difference is 2. On the other hand, 1, 1, 2, 5, 7 is not arithmetic since the differences vary. Now, given an integer array nums, the goal is to find the number of all arithmetic subsequences in nums. A subsequence is formed by removing some elements from the array without changing the order of the remaining elements. For instance, 2, 4, 6 is a subsequence of 1, 2, 1, 4, 6. The answer must fit within a 32-bit integer, and the input array has constraints ensuring it has between 1 and 1000 elements, with each element lying between -2 to the power of 31 and 2 to the power of 31 1. The output for the problem is a single integer, which represents the total number of arithmetic subsequences in the given array. Let's look at an example. If the input array is nums equals 2, 4, 6, 8, 10, the output would be 7. This is because there are exactly 7 arithmetic subsequences in this array. These include 2, 4, 6, 4, 6, 8, and others, which we will list in detail. Remember, an arithmetic subsequence requires at least 3 elements, and the difference between consecutive elements must be constant. Continuing with the example nums equals 2, 4, 6, 8, 10, the complete list of arithmetic subsequences is 2, 4, 6, 4, 6, 8, 6, 8, 10, 2, 4, 6, 8, 4, 6, 8, 10, 2, 4, 6, 8, 10, and 2, 6, 10. This brings the total count to 7. Each of these subsequences satisfies the condition of being arithmetic, or the differences between consecutive elements are constant. Notice that subsequences may vary in length, as long as they contain at least 3 elements and maintain the arithmetic property. Now, consider another example, nums equals 7, 7, 7, 7, 7. The output for this case is 16. Here, any subsequence with 3 or more elements is arithmetic because all the elements are identical, and the difference between consecutive elements is always 0. This symmetry leads to a large number of valid subsequences. Specifically, there are 16 distinct arithmetic subsequences of size 3 or more that can be formed from this input. Finally, let's examine the constraints and additional notes for the problem. The input array can have a length between 1 and 1000, and elements range from -2 to the power of 31 to 2 to the power of 31 1. The output must fit within a 32-bit integer. Subsequence elements do not need to be contiguous, and arithmetic subsequences must have at least 3 elements. The optimal solution for this problem has a time complexity of n squared. Key edge cases include arrays with fewer than 3 elements, which should return 0, and arrays with identical elements, which can have many valid subsequences due to their symmetry. These details help ensure a comprehensive understanding of the problem and its constraints. To begin solving this problem, the most intuitive approach is the brute force method. Here, we generate all possible subsequences of the given array, and for each subsequence, we check whether it forms an arithmetic sequence. While this method is straightforward and easy to understand, it comes with a significant drawback. Generating all subsequences requires 2 to the power of n time, as the number of subsequences grows exponentially with the size of the array. Additionally, for each subsequence, we need to validate if it is arithmetic, which takes k time for a subsequence of length k. When combined, the total time complexity becomes n*2 to the power of n, making this approach computationally infeasible for larger inputs. This highlights the need for a more efficient solution. Now, let's look at an optimized solution using dynamic programming and hash maps. The key observation here is that instead of evaluating all subsequences globally, we focus on subsequences that end at a specific index. For any 2 indices, I and j, we calculate the difference, d, as nums I, nums j. Then, we use a hash map, dp, I, to store the count of arithmetic subsequences ending at index I with a specific difference, d. For every pair of indices, if the difference, d, already exists in dp, j, we can extend those subsequences to include nums, I. We update dp, I, d, by adding this count and include the new subsequence formed by nums, j, and nums, I. This approach avoids explicitly generating all subsequences, instead building the counts dynamically as we iterate. The overall time complexity is reduced to n squared, thanks to the nested loops and efficient hash map operations, making it a practical solution for the problem. Dynamic programming was chosen for this problem because it provides a significant efficiency advantage over brute force. By focusing on maintaining counts of potential subsequences directly, we eliminate redundant calculations. Using hash maps allows us to efficiently track differences in subsequence counts at each index, resulting in a manageable n squared time complexity. When comparing approaches, brute force is simpler conceptually but impractical due to its exponential complexity, especially for larger inputs. Alternatives like backtracking were also considered but dismissed, as they struggle to handle overlapping sub-problems effectively. The dynamic programming approach strikes the right balance between clarity and efficiency, ensuring both correctness and scalability. This makes it the optimal strategy for addressing the constraints of this problem in a real-world scenario. To solve this problem, we need to find all subsequences of a given array that form an arithmetic sequence. An arithmetic sequence is defined as one where the difference between consecutive elements remains constant. For example, in the array 1, 3, 5, 7, subsequences like 1, 3, 5, and 3, 5, 7 qualify as arithmetic sequences because their consecutive differences are consistent, while 1, 5 does not. A brute force approach to this problem involves generating all possible subsequences of the array, which is essentially the power set, and then checking each subsequence to see if it meets the criteria for being arithmetic. The concept is simple, but the computational cost is high because the number of subsequences grows exponentially with the size of the array. To implement this, the first step is generating all subsequences. For an array of length n, there are 2n possible subsequences. A common way to achieve this is by using bit masking, where each bit in the binary representation of numbers from 0 to 2n1 indicates whether the corresponding element in the array is included in the subsequence. Once the subsequences are generated, the next step is to check each one to see if the difference between consecutive elements is constant, which confirms it as an arithmetic sequence. The final step in this brute force approach is to output all the subsequences that pass the arithmetic sequence check. These valid subsequences are stored and then returned as the result. While straightforward, this method does need to account for edge cases. For instance, arrays with 0 or 1 element are trivially arithmetic because there are no gaps between elements to check. Arrays with duplicate elements also require careful handling to ensure the arithmetic difference is calculated accurately. Now, let's talk about the key operations involved in this approach. Generating subsequences using bit masking takes 2 to the power of n*n time because we are iterating over 2n combinations, and each subsequence can take up to n time to construct. For the arithmetic check itself, we verify the difference between consecutive elements, which takes k time for a subsequence of length k. While this brute force method is clear and easy to implement, its high computational cost makes it impractical for larger arrays. This opens the door for more optimized solutions. To implement the brute force approach, we rely on a few key data structures. The original array is stored as is, while subsequences are generated using bit masking, which provides an efficient way to iterate through all possible combinations of array elements. The valid arithmetic subsequences that pass the checks are then stored in a list of lists for output. However, generating all subsequences inherently leads to exponential growth in computation, making this approach infeasible for larger inputs. This is where optimizations come into play. By leveraging techniques like dynamic programming or hash maps, we can store previously computed results, reducing redundant calculations and improving efficiency. Sorting subsequences, if needed, can also help simplify the arithmetic check by ensuring that the sequence is ordered. The optimized approach utilizes dynamic programming to count and generate arithmetic subsequences without redundantly checking the same combinations multiple times, significantly reducing the time complexity compared to the brute force method. The brute force method has a time complexity of 2 to the power of n*n, because generating subsequences and checking each one for an arithmetic pattern are both computationally expensive steps. The space complexity is also 2 to the power of n, due to the storage required for the subsequences. To illustrate this approach with an example, consider the input array 1, 3, 5. First, we generate all possible subsequences 1, 3, 5, 1, 3, 1, 5, 3, 5, and 1, 3, 5. Then, we check each subsequence to determine which ones are arithmetic. Subsequences like 1, 3, and 3, 5 are valid because their differences are consistent at 2. Similarly, 1, 3, 5 also qualifies as arithmetic with the same constant difference. However, 1, 5 does not meet the criteria since the difference between its elements is not consistent. The valid subsequences are 1, 3, 3, 5, and 1, 3, 5. While this example demonstrates the process clearly, the brute force approach's inefficiency becomes apparent for larger inputs, highlighting the need for a more optimized solution using dynamic programming. The provided solution efficiently calculates the total number of arithmetic subsequences in the given list nums using dynamic programming. Here's a detailed explanation. 1. Initialization. The code starts by checking if the array length is less than 3. Since an arithmetic sequence requires at least 3 numbers, we immediately return 0 for such cases. A list DP of dictionaries is initialized. Each dictionary at index I tracks the count of arithmetic subsequences ending at nums, I, for every possible difference. 2. Outer loop. The outer loop iterates over each index I in the array, representing the current end of a potential arithmetic subsequence. 3. Inner loop. The inner loop iterates over all indices j before I, representing the second to last element of a subsequence ending at nums, I. For each pair, nums, j, nums, I, the difference diff is calculated. For updating dp, I, the count of subsequences at dp, j, diff, is fetched. This represents the number of subsequences ending at nums, j, with the same difference. These subsequences can be extended with nums, I, so we add count _add _j to dp, I, diff. Additionally, the pair nums, j, nums, I itself forms a new subsequence of length 2, so we increment dp, I, diff, by 1. 5. Counting valid subsequences. While updating dp, I, diff, we only count subsequences of length 3 or more, i.e., count _add _j, towards the result. This ensures that shorter subsequences are not included in the total count. 6. Return result. After processing all pairs, the variable total _count contains the total number of arithmetic subsequences of length 3 or more. This value is returned as the result. ### time and space complexity. Time complexity. The solution has a time complexity of n squared, where n is the length of the array. This is due to the nested loop structure. Space complexity. The space complexity is n*d, where d is the number of unique differences. In the worst case, this can be close to n squared. This approach is efficient and handles all edge cases, including arrays with repeated elements or large differences. Here, we start by importing the necessary libraries and defining our solution class. The goal is to find the number of arithmetic subsequences in the given array. First, we check if the array's length is less than 3 because an arithmetic subsequence requires at least 3 elements. If that's the case, we immediately return 0. Next, we create a list of hash maps, called dp, where each hash map corresponds to an index in the array. These hash maps will store the difference between elements as keys and the count of subsequences with that difference ending at the current index as values. This allows us to efficiently track the arithmetic sequences as we iterate through the array. We then initialize a variable total count to keep track of the total number of valid subsequences. Now, we begin the nested loops. The outer loop iterates over each element in the array, while the inner loop examines all previous elements to calculate the difference between the current and earlier values. This difference, stored in the variable diff, is crucial because it helps us identify and extend arithmetic subsequences. Next, for the difference at the earlier index, we fetch the count of subsequences that end there using dp.get, j.get or default, diff, 0. This count represents all subsequences that can be extended by including the current element. We then update the hash map for the current index to include this difference. Specifically, we add the count of subsequences ending at the earlier index, count at j, and account for the newly formed subsequence consisting of just the two elements at indices j and I. By doing this, we ensure that all subsequences ending at the current index are tracked. Importantly, we only add to our total count if the subsequence has a length of at least 3. This is because sequences of length 2 are not considered arithmetic subsequences for the purpose of this problem. The total count variable accumulates the count of valid subsequences as we process each pair of indices. Finally, once all pairs have been examined, we return total count, which represents the total number of arithmetic subsequences in the array. This implementation is efficient, leveraging dynamic programming and hash maps to avoid redundant calculations and ensure that we handle all possible subsequences systematically. Here, we begin with an example input array nums equals 2, 4, 6, 8, 10. First, we initialize n to the length of the array, which is 5. We also set up a list of dictionaries called dp, where each dictionary will keep track of the count of arithmetic subsequences ending at a specific index with a given difference. Additionally, we introduce total_count, initialized to 0, which will store the total number of valid arithmetic subsequences of length 3 or more. Now, we iterate through the array with an outer loop over I, where I represents the ending index of a subsequence. For I equals 1, we evaluate all previous indices j. At j equals 0, we calculate the difference diff between nums, 1, and nums, 0, which is 2. Since no subsequences with this difference exist ending at index 0, count_at_j is 0. We then update dp, 1, 2, to include this new subsequence and increment its value by 1. At this point, there are no valid subsequences of length 3, so total_count remains 0. The intermediate state of dp reflects this update, showing that a subsequence with difference 2 now ends at index 1. Next, for I equals 2, we check all preceding indices. Starting with j equals 0, the difference diff between nums, 2, and nums, 0, is 4. As there are no subsequences with this difference ending at index 0, count_at_j is 0. We update dp, 2, 4, by adding 1 for this new subsequence. Moving to j equals 1, the difference diff between nums, 2, and nums, 1, is 2. Here, count_at_j is 1 because there's a subsequence of difference 2 ending at index 1. We extend that subsequence and also add a new one, resulting in dp, 2, 2, being updated to 2. Importantly, since we extended an existing subsequence, we increment total_count by count_at_j, bringing it to 1. The intermediate state of dp now shows subsequences with differences 2 and 4 ending at index 2. This process highlights how the algorithm tracks and builds upon existing subsequences. For I equals 3, we repeat the same process for all previous indices, calculating differences and updating the dp states. At the end of this step, the dictionary for index 3 shows counts for subsequences with differences 2, 4, and 6, specifically dp, 3, 2, equals 3, dp, 3, 4, equals 1, and dp, 3, 6, equals 1. The total_count is updated to 4, as we've extended multiple subsequences to reach the required length. Finally, for I equals 4, we perform similar calculations across all preceding indices. The final dp4 index 4 contains counts for differences 2, 4, 6, and 8, with dp, 4, 2, equals 6 being the most significant. This means we've extended many subsequences with difference 2 to reach the current index. By the end of all iterations, total_count reaches 7, representing the total number of valid arithmetic subsequences of length 3 or more. The output for this example is therefore 7. Now, consider another example with input nums equals 7, 7, 7, 7, 7. After initializing n, dp, and total_count, we start iterating. For I equals 1, we calculate the difference between nums, 1, and nums, 0, which is 0. Since no subsequences exist yet, we simply update dp, 1, 0, to 1 to account for this new subsequence. At I equals 2, we evaluate indices j equals 0 and j equals 1. For j equals 1, the difference is again 0. Here, we extend the subsequence ending at index 1 and update dp, 2, 0, to 3. This includes both new subsequences and extensions of existing ones. Additionally, because we've extended at least one valid subsequence to length 3 or more, we increment total underscore count to 1. The intermediate states of dp reflect the growing counts of subsequences with the same difference. For I equals 3 and I equals 4, we continue extending subsequences in a similar fashion. Since all elements are identical, the difference remains 0 throughout. At index 4, dp 4, 0 accumulates to 15, representing all possible subsequences with this difference. The total underscore count reaches 16, which includes all valid arithmetic subsequences of length 3 or more within the array. Finally, in the third example with input nums equals 1, 2, 3, 4, 5, following the same steps, the algorithm builds subsequences with difference 1. At index 4, the dp state shows dp 4, 1 equals 7, and total underscore count calculates to 6. This value represents the total number of valid arithmetic subsequences of length 3 or more, and thus the output is 6. Each example demonstrates how the dp approach efficiently tracks and counts subsequences. The time complexity of the solution is n squared, where n represents the length of the input array, nums. To break this down, the outer loop iterates through each index I in the array, which accounts for n. For each of these iterations, there is an inner loop that processes all indices j before I, effectively creating a triangular series of iterations. The number of total iterations across all pairs, I, j, sums up to the first, n1, integers, which can be calculated using the formula, n1, n/2, simplifying to n squared. Within the inner loop, operations like calculating the difference between elements, updating the dp structure, and incrementing the total count are all constant time, or O1. Since the nested loops dominate the runtime, the overall time complexity is n squared, in the best, average, and worst cases. This consistency arises because the algorithm processes all pairs, I, j, regardless of the input distribution. The space complexity of the solution is n squared, in the worst case, though actual memory usage is often much lower in practice. The primary contributor to this complexity is the dp array, which consists of n dictionaries. Each dictionary maps a difference value, diff, to the count of arithmetic subsequences ending at a particular index with that difference. In the worst case, every pair, j, I, might have a unique difference, leading to up to n keys per dictionary. When multiplied across all n dictionaries, this results in n squared space. Additional variables like total underscore count, diff, and loop counters use constant space, or O1. However, in practical scenarios, the number of unique differences is often much smaller than n, especially if the input array contains small or repetitive values. This reduces the space required for the dictionaries, meaning that while the theoretical upper bound is n squared, the actual memory usage is frequently much lower. When comparing this solution to a brute force approach, the improvement in efficiency becomes clear. A naive method would involve generating all possible subsequences of the input array, which amounts to 2 to the power of n subsequences, and then checking each one for the arithmetic property. Verifying a single subsequence of length k would take k time, leading to an overall exponential time complexity of n*2 to the power of n. In contrast, the optimized approach leverages dynamic programming to count arithmetic subsequences efficiently in n squared time. This quadratic complexity stems from iterating over all pairs, I, j, and performing constant time operations for each pair, eliminating redundant recalculations. On the space side, the brute force method requires only n space to store a single subsequence during its checks, but its exponential time complexity makes it impractical for larger inputs. The current solution trades this minimal space usage for a higher but manageable n squared space complexity, resulting in a much more feasible approach for larger datasets. When tackling this problem, there are a few common mistakes that candidates should be aware of. First, it's crucial to fully understand the problem statement, particularly whether the sequence needs to be contiguous or can be non-contiguous. Misinterpreting this can lead to implementing a solution for the wrong problem, which wastes valuable time during an interview. Next, overlooking edge cases is another frequent issue. Scenarios like single-element arrays, empty arrays, or arrays where all elements are identical often trip people up. Missing these cases can result in runtime errors or incorrect outputs, which can be costly. Another mistake is using inefficient implementations, such as brute force, to generate all possible subsequences. While this might work for small inputs, it quickly becomes infeasible for larger datasets due to excessive time complexity, often leading to time limit exceeded errors. Finally, failing to correctly verify the arithmetic properties of a sequence, such as calculating or comparing the common difference inaccurately, can lead to logical errors, producing false positives or negatives when determining valid sequences. Another important consideration is space complexity. Many solutions rely heavily on recursion or auxiliary storage without accounting for the associated space trade-offs. This can become problematic for larger inputs, as high memory usage may lead to memory limit issues. To excel in interviews, it's helpful to focus on a few key insights. Recognizing patterns early is essential. Many problems involving arithmetic sequences can be reduced to analyzing the differences between elements, which can save significant time. While a brute force approach might help you understand the problem initially, it's important to optimize quickly by reducing unnecessary computations. Techniques like dynamic programming or sliding windows can be very effective here. Testing edge cases is another critical step. Examples like empty inputs, arrays with uniform values, or minimal sizes should always be considered before finalizing your solution. Lastly, effective communication is key. Clearly explaining your thought process, especially when weighing trade-offs between time and space complexity, demonstrates a strong understanding of the problem and builds confidence with your interviewer. For further practice, there are several related problems you might find helpful. Examples include LeetCode 1027, which focuses on finding the longest arithmetic subsequence, and LeetCode 413, which explores arithmetic slices. Additionally, LeetCode 1218 deals with the longest arithmetic subsequence of a given difference, and of course, LeetCode 446, which is the focus of this tutorial. When thinking about solving these types of problems, there are multiple approaches to consider. A brute force method involves generating all possible subsequences and checking each for arithmetic properties. While simple to implement, this approach is highly inefficient due to its exponential time complexity. A more practical solution is dynamic programming, where you use a DP table to track the length of arithmetic subsequences ending at each index. This is significantly more efficient, with time complexities around O, n squared, or even O, n, for certain variations, though it does require careful implementation. For even greater efficiency, you can use a hash map to dynamically store differences and their counts. This approach can achieve linear runtime for some variants, making it both memory efficient and fast, though debugging it can sometimes be challenging. Understanding these trade-offs will help you choose the best approach for a given problem. Great job following along. To summarize, we tackled the problem using a dynamic programming approach with hash maps to optimize for both time and space. Remember to apply these concepts to similar problems, and keep building your problem-solving skills. Thanks for watching, and see you in the next tutorial. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!